So, sir, my next question to you would
Yes.
be, uh, your primary research focus has been the behavior of hadrons in extreme conditions. Could you shed some light on it? Like, how do hadrons behave in extreme conditions? Like, uh, what's the current state of this field, and how much uh, discovery, or how much progress have we made in this field?
Okay. Uh, so I can give you a general idea, and then I will answer only about hadrons. So when we talk about strongly interacting physics, we think in terms of a QCD phase diagram, which is a plot between temperature and baryonic chemical potential. We can think like temperature and baryonic density as temperature as a y-axis and baryonic density as a x-axis. So what we try to understand is like how matter behaves, whatever matter it is. It could be hadronic matter, it could be a quark matter. So whatever matter it is, how it behaves under such temperature. When we talk about 200 mega electron volt, when we talk about 1 to 10 times nuclear saturation density. Nuclear saturation density is the density of a nucleon. So when we talk about such kind of matter, like we have an idea, like theoretical idea. We took insight. We have like the scientists take insight from like other theory like condensed matter physics, as well as like simple thermodynamics, like how the matter could behave at such high temperature and baryonic density, and they anticipate like we have a water phase diagram, we have a solid, liquid, and gas phase. Similarly, in when we talk about strongly interacting matter, there could be a phase transition of hadron to quarks. So when we talk about quarks, so quarks are like indivisible particles. They are lower in the edge. They are the endmost particle. And if you compress hadrons more, if you compress more in such a high temperature and density, the hadrons will get converted into quarks. This is a very simple, reasonable explanation. So what we try to understand in what condition, what is the phase transition line where where these hadrons get converted into quarks. This is one thing we want to understand in the strong interaction physics, which is called first order phase transition line. And similar to uh, water diagram, we have a critical point where two phases can coexist. So we are also interested in the criticality of QCD phase diagram where the hadronic phase as well as the quark phase can coexist. So this is just a introduction to the answer you wanted to ask. But about the hadronic part, now I can answer better. So in the hadrons, like we have mesons, we have baryons. And when the baryons interact with matter, it can change its properties. Like baryons have certain mass, like nucleon have mass like around 939 MeV. But when it interacts with temperature, when it interacts with the density or magnetic field, it can change the mass of that particle. It can the extremity of the surroundings can change the behavior of the particles, like mass, decay width. The mass we are talking about, like 939 MeV, is at vacuum. So we try to understand in my PhD when I calculate the properties of in medium hadrons. I try to understand like how the properties of some mesons like J psi epsilon states changes with medium when they interact with hot and dense matter and magnetic field as well. So what it can tells us, it can have a signature of J psi separation. So I will not go in detail, but like it tells us about what happens inside the heavy ion collision. So in heavy ion collision, we are trying to create a mini Big Bang, right? So in the mini Big Bang, we try to understand. So there is no way we can understand what is happening inside the quark gluon plasma because the time is very fast there. It happens quickly. When I say quickly, it is like 1 Fermi by C. So we cannot directly understand what is going on in that fireball. So we need to use some method like some reverse engineering. So we understand the hadron properties like the particle decays and all that, and we try to extrapolate in the backward direction. Okay, this could be the reason what happened in quark gluon plasma, and then we have an understanding. Okay, what is happening inside that fireball?
So it's like observing the shattered remains of an accident site and trying to reconstruct the accident, right?
Yes,
So,
very true. For example, a quick note. When we talk about vector mesons, so we call it the vector mesons like decay into dileptons. So dileptons are electron and electron positive, let us say. An electron positive and electron doesn't participate in strong interaction. It doesn't interact with strong interaction. It only interacts through the weak interaction or electromagnetic. So if it does not interact with the strong interaction, so its properties, which was initially created due to strong interaction, and it is traveling through the medium, it will never change. So the electrons are containing that all the information what happened inside the collision. So this is very intrinsic, the very, very important property of meson decay.
So while discussing this, an interesting unit came up. You mentioned that the time interval is too short and it's shorter than Fermi per what you said. I can't
C.
recall. Fermi per C.
Yes.
So is it a unit of time? I never heard of
Yeah,
this
it's a unit
unit.
of, when we talk about heavy ion collision, this is the most convenient unit of time. Then we can say it is 1 Fermi by C or 2 Fermi by C. Otherwise, we have to deal with like numbers, huge numbers.
I see. So yeah, I totally didn't know about this unit of time. Uh, I was familiar with Planck time, Planck length, but I will guess that Planck time is far shorter interval than Fermi per se.
Yeah,
Am
that
I
is
right?
on the extreme limit. Yeah, that should be, obviously that should be shorter than that.
Okay. So uh, is it justified if I say that we know sufficiently enough about the behavior of hadrons in extreme conditions? How hadrons behave in extreme conditions? Would it be justified if I say that we know sufficiently enough, or would that be a display of overconfidence?
No, not at all. We know like we don't know like 1% of what is really happening. I will tell you why I'm saying that. Um, we have to think in terms of experiments. So right now, in the last 2 decades, like from not two to last 2 or 3 decades, more money is put into understanding what is on the strong interaction level. More money is put into LHC, CERN, as well as Brookhaven National Laboratory to understand heavy quarks, to understand heavy states, which exist at very high temperature and low density. So we, in the QCD phase diagram, the experiment have only covered the high temperature and low density part of the strongly interacting matter. So we have evidence there. And rest of the QCD phase diagram is being explored by the theoretical models. And when we talk about theoretical models, in quantum chromodynamics, we are limited. So for example, I will take the example of nuclear physics. So everything was very good up until thermodynamics, statistical physics, condensed matter physics, and everything. And then this nuclear physics comes up. And you cannot apply the one single model to explain the nucleus. So you have to rely on different models. Like, okay, let's talk about the saturation property. Okay, liquid drop model. Let's talk about the how the energy levels of the nucleon. Then shell model. How the atom is vibrating. Okay, vibrational model. So you cannot develop a single theory in nuclear physics to describe the nucleus property. And same thing happened in the quantum chromodynamics or strong interaction physics due to the coupling constant of strong interacting matter, strong interacting physics, because the coupling constant is it is like feeble, very feeble, weak in the quark regime, but in the hadronic regime, it is very high. So it is very hard to apply a single theory on the whole QCD phase diagram. And we have a theoretical limitation. So we cannot apply pure QCD theory in the all range. We can only apply into high temperature and high baryonic density. As, on what we can rely on, right? We can only rely on good theory as well as experiments. So the good theory has a limitation, and experimental experiments have also some limitations, and we have not explored enough in the high density side of it. But right now, in the next coming few years, like scientists have invested huge into creating a moderate temperature and high density baryonic or quark matter. For example, there's a panda in Darmstadt, as well as panda experiment in Darmstadt, GSI Helmholtz, and also in Japan, J Park, Nika in Dubna, Russia. They are more focused into fixed target experiments, which can create create a matter which have moderate temperature like around 100 MeV and the baryonic density, high baryonic density around 4 to 5 nuclear saturation density or more. So with that experiment, we will get to know, okay, what kind of models, whatever they are predicting is true. So right now we have like 100,000 of model and everybody is predicting the best out of their model. And with time, when we have more experiments, we will get to know like who was good enough to predict the actual or who is more close to the actual result.
So the current situation in particle physics is like this. Like there are various models, then we have predictions of those models, and then we have these places like CERN who are doing particle collider experiments and testing these models, and based on the uh, results of these tests we are able to eliminate some of the previously existing models, right? So we don't have a firm model right now.
Yeah. In terms of non-perturbative regime hadronic physics, we do not have like you have like put a very great idea or concept about the LHC CERN. So when we predicted like Abdus Salam model predicted this SU3 weak the electroweak theory, and it predicted okay there is a weak W plus minus Z boson, and I guess CERN predicted that if I am not wrong, and it was very close. Okay, then we say okay we have some theory that is backed by experiments. Similarly, in the high, moderate temperature and high density environment, when we have a experiment in future, then we will get a better idea. So it doesn't, it works like back and forth. We have experiments, experiment gives us some input, we improve our model, we throw some result. It is like a back and forth reaction thing. And I would like to say one thing more. So this is not like we can the models we are working on, they are good, they are based on symmetries, they are based on underlying QCD theory, but we are not sure about a particular result until we have experimental data, because every model is predicting different results. They are sometimes they are very far, some most of the time they are like predicting result in a good uncertainty band. So while calculating such kind of environment, like dense environment we have thousands or crores of particles, it is very hard. You cannot put thousand or crore particles, let's say thousand particles. Let's not go into extremity. Let's if you put thousand particles in a box in a computer simulation, it is very hard for a computer to compute such calculation. It will take years to do that. So we rely on simple assumption to calculate that. So we have technological limitations as well. So it will be improved with time.
I see. So based on that, what would what would your position be on the statement that, the testing of these models rely heavily on how much, what are the limitations of these uh, experiments? And in particle physics, I have heard that bigger the particle collider, better the results, or something like that. So, uh, in order to achieve that, we need more funding going into these experiments. And so, if I say that the veracity of these models rely on the experiment and the experiments rely on the funding, would you say that these particular field is getting sufficiently funded so that you can continue or carry out your research in ease?
Okay, you want an honest answer or you want a diplomatic answer?
Okay, both would be like both would be great.
Okay, so what I've observed from like going into different conferences, like scientists are more into the neutron star or compact star properties, especially neutron star mergers nowadays. So the fundings has been reduced to the um, traditional like heavy ion collision in the moderate temperature as well as the high density regime. So people are waiting from lattice QCD to confirm whether there is a phase transition. So lattice has certain limitation which is trying to overcome. The people of lattice like are trying to overcome. So there is a huge budget cut in the particle physics. What I have heard, I am not, like a new, what do you call this, correspondent of some news channel. So I don't know much. I have like little knowledge about that. But from my understanding, the funding has been gone down a lot in the pure physics area. So people are more into the applied part of it. Like how can you get how can you made something which will be directly useful to the public, right? And we are more focused into the era of AI. Like we want to use machine learning algorithm as well as statistical analysis to our research to kind of be updated in the field of physics. As you know, this year, 2024 Nobel Prize was given in the field of AI. I'm still trying to understand how it is connected to physics. I have not much done much research, but I will go through that. So, but I personally feel that like this is the call of the hour. We have to integrate such techniques like AI, machine learning, statistical analysis into our current research, and that will be funded, and that the government or the people or the professors are focusing on.
So, like every other businesses or industries, scientists would also have to, go with the AI trend to get their research funded. So, do you see in
Yeah.
near future like a sufficiently strong AI that is doing your job, like coming up with models and coming up with predictions?
Um, I believe that research would be the last resort that AI will break into. So my reasoning is that like as a researcher, we don't know what we are doing. So we try to understand things and we learn every day. We try to handle problem every day. So it is not preset. So the AI can give us, we can use AI for sure. We can use ChatGPT, we can get inferences from that. So when we talk about a physical problem, we are talking about a 10,000 lines of a code. So which is, I mean, I'm giving an naive example. So my code is like around 10,000 lines in Fortran. So ChatGPT or anything cannot give me that code that big.
So, so my next question to you would be that in researching the behavior of hadrons in extreme conditions, and the term quark gluon plasma came up quite a number of times. So, is it safe to say that you are actually studying the behavior of the quark gluon plasma in extreme conditions, or the quark gluon plasma is the extreme condition that you know affects the hadrons in it?
Okay. It's a game of nomenclature. So how do you say it? So I would say when I say extreme condition, I'm talking about the variables or parameters like temperature, density. So it could be of quark gluons or it could be of hadrons. Yeah, quark gluons are extreme in a sense that it is the very first stage after the radiation era. It is the very first stage that universe got into. And quark gluon's plasma is very dense and at very high temperature. So in that sense, we can say it is extreme. And from that, like if we talk about like a Big Bang theory, with the passage of time, when the area expand, the quark gluon plasma is losing the energy with time, and it eventually forms it got converted into hadrons or due to the formation of bound states into hadrons.
Okay. So, sir, how does the current understanding of the quark-gluon plasma and its behavior help us in understanding the early universe, like the very first, you know, moments just after the Big Bang?
Um, okay, well, this is not my area of expertise. It is more like a cosmological question. So people are more interested into the inflaton model, if I'm saying it right. In the inflation period, that was the period which, after the Big Bang, the universe grew up suddenly, like it inflated in a second. It gets in from nothing to radiation dominated area, then it gets converted into the matter dominated area. So it is more like a inflaton model people are working on in the cosmological side, and I think it can be related to the string theory or quantum gravity, I'm not sure. I'm not the expert, as I told you. But from the particle physics side, the nuclear physics side, it is beyond the scope of what we are trying to do here. We are more into the well-established quark-gluon plasma, and then the hadron formation from it.
I see. So uh, it is, I can say that the current understanding of quark-gluon plasma can be applied to understand you know, the very first moments of Big Bang, right, sir?
Mhm.
Okay. So, but your area of understanding is more into like the uh, more later stages, like how it behaves in other sort of conditions.
Yeah, quark-gluon plasma is much later. If we say like inflation is very primary, and then we have a quark-gluon plasma, which is very late.
Okay. So, if I shift the question to, far later stages of the universe, like, then how does the understanding of the hadrons help in understanding the behavior of extreme stars like neutron stars and these white dwarfs? Like, how do you apply your knowledge of hadrons into understanding these stars? Like, where do you make the connection?
Yeah. That is a very good question. So let's talk about neutron stars. So when we say neutron star, we say we assume like there are only neutrons into it, like due to the nomenclature. But in actuality, in neutron star, there could be nucleons, there could be quarks in a very dense core, there could be mesons, there could be strange baryons as well. So neutron star is mainly neutrons, but all other particles as well. Um, so these particle properties get changed when it interacts with the medium. For example, meson could get condensed. They can be in a Bose-Einstein condensation state. And also, when we talk about nucleons, nucleons cannot have the same mass like 39 MeV in such condition. It would change with respect to the temperature is 0 MeV effectively. So let's talk about the density effects. So it will not stay 939. It will decrease with density as we have predicted from the models. And similarly, quarks. So the quarks are bound inside hadrons if we talk about the outer core. But when we talk about the inner core of a compact star, such as neutron stars, then the quarks are very dense, so they cannot exist like a hadrons there. So they are intermixed with themselves, and the state is we call this state as a deconfined state where quarks and gluons can roam freely. So which can be understood from the perturbative QCD side of it, which can give us also insight what happened at the very beginning of the universe.
I see. So with that, we come to the end of today's session. So before we end the session, sir, I would like to ask you that is there any message that you want to share with our audience?
So, as all of you are, very curious about the AI boom, I'm also very curious, and I am more into learning machine learning and statistical analysis, all this stuff, and how can I integrate into my current understanding of physics? So, this is very, very important in nowadays in the current research. So I would just give a message that everyone should look into the different tools they can use to maximize their research, and also don't plagiarize. So we have certain limits for that. So we have to use it as an assistance, not like we have to rely it complete on it completely. So that is what I think one of the main area new researchers should focus on, like how to use tools like ChatGPT and all the other AI tools into their research. And in coding, it is very, very helpful. So as a physicist, we are not well-trained coder, right? We learn in bits and pieces. We learn some part of MATLAB, we learn some part of Mathematica, we learn some Fortran. We are not properly trained like a computer scientist. But with the ChatGPT like tools, we can like ask any question to ChatGPT and give me this code, and we can develop our understanding out of it. So the next coming decade is of AI, and we need to focus on how can we implement, how can we use or milk that cow maximum to get maximum out of it.
Okay. So that brings us to the end of another enlightening episode of the ScienceOverse Expert Panel discussion with Dr. Rajesh Kumar. Thank you so much, sir, for sharing your journey and the deep insights into the fascinating world of theoretical nuclear astrophysics. To our audience, so we hope you enjoyed this session. So if you have any questions or comments, feel free to share it with us. We'd love to hear your thoughts on these episodes. So don't forget to subscribe to the Science of Us YouTube channel and follow us on Instagram for updates on upcoming episodes. And if you're new to this channel, check out the previous episodes. It, these episodes will be linked in the description of this video. So thank you for joining us on this cosmic journey. And lastly, until next time, stay curious.